Hello friends, welcome to Physics Online. From today we are going to start a series on electromagnetism, and we start our journey from a small thing called as charge. Okay, so let's begin. Now let's first define charge. So what is charge? Charge is an intrinsic property of fundamental particles. Intrinsic means that property is neither acquired nor it can be relinquished. Fundamental particles, we mean all those particles by which we make up the matter. So they could be protons, they could be neutrons, or they could be quarks, or they could be any subatomic particle which ultimately goes towards building the matter. Now, there are two types of charges, namely positive and negative. Charge possessed by the electron is taken as negative. Charge behaving differently from that of an electron is taken as positive. So that is the definition of positive and negative charges. Now, unlike charges, I mean to say, like if there is a positive charge and a negative charge, then they attract each other. Like charges, that means if there are two positive charge or there are two negative charges, they repel each other. The force of attraction or repulsion between any two charges is given by a famous law called as the Coulomb's law. We'll see about Coulomb's law at the end of this session. At the present moment, we know that the force is proportional to the product of the two charges between which the force exists, and it is inversely proportional to square of the distance between the two charges. Charges are scalar quantities. Their SI unit is Coulomb charges. CGS is stat Coulomb, or we call it as the electrostatic unit, ESU. Charges are conserved, that is the sum total of charges in this universe is a constant. So charges can neither be created nor destroyed. This is an important property which we will be covering up when we do current electricity. Now, how do you charge a body? So basically, if you take a body, it is perfectly neutral. That means it doesn't carry any charge, correct? You must have heard about charging your mobile, charging your battery and all. So how do you charge a body? Basically, there are three ways of doing it. You do it by friction, induction and conduction. Friction, simple. You take an object, two objects, and rub each other, and when you rub each of them, then there is an exchange of electron from one body to the other. Electron being negative, so if a body gives electron, it becomes positively charged, and if a body acquires electron, it becomes negatively charged. So if there is two neutral bodies, let us say that we have a silk cloth and a grass rod, and we rub them, so the rod will give out electrons to the silk cloth. So silk will become negative and the rod will become positive. So this is what is frictional way of charging an electron. That's shown over here. Say you take a positive rag and you take a neutral PVC pipe. Now you will notice that as soon as you rub it, some of the negative charges are acquired by the neutral rag. This process of charging is fundamentally called as charging by friction. Another is induction. That is, if you notice that it's a neutral charge on the left side, so the body has got equal number of positive and negative charges. The moment you bring a positively charged rod nearer to the sphere there, all the negative charges gets accumulated on the right side. That is the side which is facing the positively charged rod. Importantly note that we are not touching the two objects. The sphere and the rod are at a distance, even though they are very near to each other, but they are not meeting each other, they are not in contact with each other. So this way of inducing a charge or producing a charge in a neutral object merely by bringing a charged body near it is called the process of induction. Another form of it can be seen with a series of pictures A, B, C, D. Initially, you'll notice that there are two spheres and they are kept on an isolated stand. As you can see, there are no charges on them. When you say no charges of them, basically the total number of positive charge and negative charge in them is equal, so they are neutral. We bring a positively charged rod nearer to A, so one side of the charge A becomes negatively charged and the one side of B becomes positively charged. Now we continue to do so, and if you separate, now you remove the rod and you remove the two bodies away from each other. So one becomes negatively charged, the other becomes positively charged, and this is called the process. This is called the process of induced induction. Now remember, in induction, most importantly, we are not touching the body, it is just brought nearer. There is no contact between the two or more bodies. In case of friction, the bodies are rubbed together. There is an action which makes the charges being transferred from one body to here. Here no body is transferred, no charge is transferred. It is merely that the proximity of two charged bodies, or a neutral body and another charged body, um, brings about charging of the neutral body. The next method is conduction, where we physically touch the body. So if you look at it, the sphere on the left hand side diagram was initially neutral. You brought a negatively charged particle and touched it. The charge from the negatively charged particles went into the neutral sphere and it became negatively charged. So here the process is conduction. Remember, in conduction you need to touch the two bodies. The bodies have to be in contact with each other. If you look at the right side body, initially both the charges on the right are 0. When a 6 microcoulomb charge is touched with it, they are equally distributed, and in the next phase the second charge touches the third charge and again the charges gets redistributed. Look at the second picture again. If you look at it carefully, initially the two balls on the right hand side are of 0 charge, that means there was no charge, and the ball on the left extreme was 6 microcoulomb, 6 into 10 raised to minus 6, and it was a negative charge. It first came in contact with the sphere in the middle, so the charge got distributed between the two charges, minus 3 in one and minus 3 in the other. Then the middle sphere came in contact with the charge on the rightmost side, which was neutral, and again there was a redistribution of charge. So the three charge got redistributed as minus 1.5 microcoulomb and 1.5 microcoulomb. I suppose conduction is very clearly understood. We need to come in contact with each other. Another way of looking at it is an electroscope. An electroscope has a gold foil below. When it is neutral, it is touching each other, and there is a sphere which is neutral at present. The moment it comes in contact with a negatively charged rod, it acquires negative charge, and both the gold foils on the column get negative charge, and so they move apart from each other. So if you look at it, basically initially it was neutral, the sphere had no charge in it, and the gold foils below, which at the present moment are looking to be moving, are flat and there is no charge. The moment you bring a negative rod and touch the sphere, it acquires negative charge, and that moves down to the gold foils, and since both gold foils develop negative charge, they repel each other. And this way you can find out whether an object is charged or not. Now the most important property of charge that we will be encountering is called quantization of charge. That means whenever there is an exchange of charge, whenever charge is possessed by a body, it is always in the multiple of charge of an electron. Basically what happens is, whenever a body acquires an electron or gives an electron or possesses an electron, the charge depends upon how many electrons it has. So if it has 10 electrons, it will have charge equal to 10 times the charge of an electron. So that's written over here. So the amount of charge possessed by a body or transferred from one body to another is an integral multiple of the charge carried by an electron. So Q, or the charge at any given point of time, whether it is going from one body to another or one body is having it, is simply equal to the number of electrons that is transferred or it possesses. So N into E. Of course, the charge could be positive, then we take the E as positive. If it is negative, then we take E as negative. Remember that the value of E is 1.6 into 10 raised to minus 19. We summarize the whole set of whatever we studied, so let's begin and see that charges can neither be destroyed nor created, that is the conservation of charge. Charge possessed by a body or transferred from one body to another is always an integral multiple of the charge of an electron. Charge of an electron is taken as 1.6 into 10 raised to minus 19 coulomb. This property is also called quantization of charge. Charge is a scalar quantity and can be added like mere numbers. SI unit of charge is coulomb, CGS unit is stat coulomb or ESU. There are two types of charges, namely positive or negative. The charge carried by an electron is designated as negative. Charge opposite in character to an electron is taken as positive. So we clearly define what is positive, what is negative. There exists an electrostatic force between any two charges. Like charges repel each other, unlike charges attract each other. The electrostatic force of attraction or repulsion between two charges is given by Coulomb's law. And now it's the right time to start and study what is Coulomb's law. So basically in this picture, as you see, we see two charges Q1, Q2. We have taken them both as positive and they are kept at a distance r from each other. So now the Coulomb's law says that the force is directly proportional to the product of the charges, namely Q1, Q2, and is inversely proportional to the square of the distance between the two, that is r square. So we can say that F is proportional to Q1, Q2 upon r square. Now if you want to remove the proportionality, we'll have to add some constant over there, and that constant has a big reference to the material or the space in which you are bringing this two charge. So let's start by saying that we are doing this whole thing in air. So then the constant of proportionality is equal to 1 upon 4 pi epsilon naught. Now that's a very interesting thing. The 1 upon 4 pi is introduced because of Gauss. We were going to study Gauss theorem and it has its implications over there. Epsilon naught primarily is the electric permittivity of free space. That means it shows how much of electricity it can bear or it can have. Now suppose you have to do this whole thing in another medium, then the epsilon naught value will change. It will become something else. So for a free space, the epsilon naught or the permittivity is 8.85 into 10 raised to minus 12. The whole number, that is 1 upon 4 pi epsilon naught, will be equal to 9 into 10 raised to 9. Now that is very important when we do certain calculations. So this is Coulomb's law in a simple, straightforward scalar form. Suppose there is another medium. Now we do hold this exercise in another medium where the electrical permittivity is something else. Let us call it as epsilon naught r. Then of course, as we know, the force in that medium will turn out to be 1 upon 4 pi epsilon naught r instead of epsilon naught 0. Q1, Q2 upon r square remains the same because we neither change the r nor the q. Now if you just take the ratio of force in vacuum to force in medium, we get the ratio of permittivity of the medium upon permittivity of free space, and that is a constant which is called dielectric constant, which is very important when we study capacitance or we go to study much more things, or we study the electrical field manifestation in space or in medium. So the dielectric constant is very important. So instead of writing the absolute permittivity as ER, we write it in terms of ER is always as K times epsilon naught. So now the force in that medium can be written as 1 upon 4 pi epsilon naught or Q1 Q2 by R square, or you can merely write it as 1 upon 4 pi K epsilon naught Q1 Q2 by R square. Now here force is a vector quantity, so this whole Coulomb thing has to be transformed into a Coulomb, into a vector form. There are a few diagrams over here. So now notice that if you take two charges Q1, Q2, and we are talking about the force on the charge Q2, then it is written as force on 2 due to 1, and the force on Q1 is written as force on 1 due to 2. R1 and R2 are position vectors of the two charges with respect to the origin. The mutual position of the two charges is written as R21 is R2 minus R1, R12 will be R1 minus R2. Interestingly note that if the product of the two charge is positive, then the two forces, that is namely F12 and F21, are away from the charges. They are going away from each other. On the other hand, if Q1, Q2, the product is negative, then you notice that the forces on both the objects are coming towards each other. That is, it is an attractive force. This goes with what we have said, that like charges repel each other and unlike charges attract each other. Now we do a mathematical exercise to all these things. So here we have written that the charge q1 as a position vector r1, the charge q2 as a position vector r2. So the distance between the two charges, or the position of 2 with respect to 1, is written as r12. The force on 2 due to 1 is written as F21, and that can be mathematically written like this. Now r12 with that cap is a unit vector in the direction 1 to 2, and its magnitude is written as r12 with those two straight lines. Now if you rewrite the whole expression, writing the expression for the unit vector, then we obtain the last expression. So this is the vector form. So this is just academic, but actually when you need to do it, we need to require to know, first of all, the force is acting on which charge, what are the configuration of the two charges, whether they are both positive, when they are both negative, or if one is positive and one is negative, and accordingly, according to the product, if both are positive, of course they will repel. If both are negative, they will repel. If one is positive, one is negative, then they will attract, and accordingly will determine the direction of the force. So that's all about charges, and in the next class we will do a few more examples which will look at all the salient features that we have studied in this class. Thank you once again, and see you soon in the next class. That will be to do with some examples on these charges. Thank you.